Good day, everyone. Today, our group represents our project titles Electromagnetic Coupling Between Two Coils based on Faraday's law. I am Mabel Gore, and together with me, I have Michelle, Muradi, Haidia, and Isaac in this group experiment. This experiment demonstrates the concept of electromagnetic inductions, where a charging magnetic field can produce an inducive voltage in a nearby conductor. According to Faraday's law, when the magnetic flux through a coil changes, an electromotive force or EMF is generated. The main objective of this project is to observe how electrical energy can be transferred wirelessly from a transmitter coil to a receiver coil through electromagnetic coupling. In this setup, the transmitter coil produces a changing magnetic field, where the receiver coil captures this magnetic energy and convert it back into electrical energy to light up an LED.
Here is the main material and equipment that we use, which is the coil, 2N222A transistor, 27K ohm resistor, LED, 9-volt battery, and oscilloscope. The screen above shows the circuit connection, which have divided to two main parts, the receiver coil and transmitter coil. The transmitter coil is formed by the battery, transistor, the transmitter coil, and also the resistor. So first, the emitter of the transmitter connect to the negative terminal of battery. Then the base connect to the resistor, then to the coil. The collector connect directly to the coil. And for the receiver coil, the LED is connected to the coil directly. Here is some safety precaution should be noted in the lab. First, avoid short circuit when connecting the wire. Second, do not touch transistor and coil if they become hot. Third, turn off battery before modifying the circuit. Fourth, use resistor to limit current flow. And the last, handle wire carefully to avoid lost connection.
Now let's observe the electromagnetic coupling in practice. By using a battery-powered oscillator circuit, we convert steady DC power into an oscillating current, creating a time-varying magnetic field around the transmitter coil. Notice as the distance decreases, the LED intensity increases significantly. This happens because the magnetic flux linkage between the two coils is strengthened as they come into closer proximity, directly validating the principle of Faraday's law. While the LED provides a clear visual indicator, we are also capturing the precise induced voltage on this oscilloscope. You will notice the output is not perfectly linear.
Through this experiment, we can analyze the key factors that directly affect the induce of electromotive force. The first major element is the distance between the transmitter and the receiver's coil. When they are closer together, you get a much higher voltage because almost all the magnetic field lines hits the receiver coils directly, making the LED very bright. But as you pull them farther apart, that magnetic field spreads out and misses the coil, causing the voltage to drop and the LED to dim or turn off completely. Next up is alignment, or the angle of the coils. To get the best results, the two coils need to face each other perfectly flat at a 90-degree angle. If you tilt or misalign even one of them, those magnetic field lines will miss the receiver loop, which immediately drops the voltage and dims the LED. Finally, we have the numbers of turns on the receiver's coil itself. More turns equal a higher voltage, since more loops of wire are there to catch and trap the magnetic field line, pushing more electrical power to the LED. On the flip side, fewer turns mean less collected magnetic energy, giving you a lower voltage and a much dimmer LED.
In conclusion, we successfully visualized Faraday's law and quantify the impact of distance on inductive coupling. However, we observe the real-world limitation. Coupling efficiency is highly sensitive to the distance and coil alignment, with minor deviation caused by internal coil resistance and magnetic flux linkage. Understanding this factor is crucial for designing real-world system. Thank you for your time.